Every time a database query returns an ordered list or a web application ranks search results, an algorithmic sorting process is firing under the surface. At a massive scale, organizing chaotic data is one of the most resource-intensive operations a computer performs. Within the divide and conquer paradigm, two algorithms dominate this space: merge sort and quicksort. Because they are so ubiquitous, a standard technical interview question is simply to ask a candidate, which of these two algorithms is better? Replying with a definitive choice immediately fails the question. A simple algorithm X is faster ignores the specific engineering constraints required to build real-world systems. To evaluate these correctly, we look at this comparative breakdown. The first two evaluation vectors are theoretical time complexity, how fast the algorithm scales, and its physical memory footprint, or space. Next, we measure algorithmic stability, followed by the structural nature of the input data itself. There is no universally perfect sort. Designing an optimal system requires selecting the correct mathematical trade-offs for your specific environment. On screen, identical unsorted arrays demonstrate how each algorithm approaches the problem. Merge sort uses a divide-first architecture, recursively cutting the array in half until reaching single elements. During the merge later phase, it builds the sorted sequence from the bottom up. Conversely, quicksort uses a partition-first architecture. It selects a pivot number, immediately throwing smaller numbers left and larger numbers right, before recursing downwards into the subarrays. Merge sort executes its sorting work at the very end of the recursion tree. Quicksort executes its sorting work at the very beginning. We can translate these structural differences into theoretical speed limits using recurrence relations. This recurrence equation maps merge sort. By cutting the dataset perfectly in half every iteration, the recursion tree remains entirely balanced, resulting to an optimal time complexity of n log n across best, average, and worst-case scenarios. Quicksort's average case mathematically mirrors this. Assuming the pivot reliably splits the data into relatively even halves, we get a balanced tree and an n log n result. But quicksort carries a mathematical vulnerability: poor pivot selection. If the array is already sorted and the algorithm repeatedly picks the largest or smallest element as the pivot, the partitions become completely unbalanced. Look at the worst-case relation. Instead of dividing the work by 2, it only reduces the work by 1 element per iteration. The recursion tree degrades into a straight vertical line, creating a severe drop in performance and forcing an n-squared time complexity. Therefore, if a critical system requires an absolute unbreakable guarantee on its maximum computing speed, merge sort defeats quicksort every time. Speed is only 1/2 of the computation equation. We also must evaluate physical memory footprints, which introduces the in-place property. This diagram maps merge sort's memory requirement. To safely combine elements without overwriting unread data, it demands a completely separate temporary array equal in size to the original. This extra O of n storage makes merge sort not in place. Quicksort approaches this differently. By sliding pointers and swapping elements strictly within existing memory boundaries, it requires no duplicate array. It only consumes O log n space for its recursion stack, granting it the in-place property. For embedded systems with strict memory constraints or environments processing massive datasets, quicksort holds a distinct advantage. The next vector is algorithmic stability. A sorting algorithm is stable if identical input elements retain their exact original relative order after the sort is finished. Imagine a database of students who are already sorted alphabetically by their last names. If you initiate a new sort to rank them by their test scores, you want the students with tied scores to remain in alphabetical order. Looking at this array, merge sort sequentially resolves elements through adjacent pairing, mathematically preserving the original order of duplicate values like these 50s. Quicksort lacks this sequential caution. Its partition logic relies on long-distance swaps across the array. throwing elements past one another to clear the pivot line. This leapfrogging inverts the order of identical elements, making it unstable. If your data contains secondary metadata layers that cannot be scrambled, you must reject quicksort and implement merge sort. While merge sort provides better theoretical guarantees and stability, production languages like C++, Java, and Python still default to quicksort for standard arrays. Theoretical Big O notation measures operations, but it ignores the physical architecture of modern processors. CPUs load data into fast, local memory pools called caches. Quicksort possesses high cache locality. Because it reads and swaps data sequentially inside a single array block, the CPU processes the memory continuously without pausing to fetch new data. Merge sort constantly jumps back and forth between the original array and the temporary array. This physical jumping causes expensive hardware cache misses, slowing down the processor in real-time execution. There is one major exception to this rule. This is a standard linked list data structure. By definition, linked list nodes are scattered randomly throughout computer memory. Cache locality is irrelevant here. Furthermore, merge sort can process linked lists simply by redirecting the pointer arrows, completely bypassing its usual memory penalty. Quicksort leverages physical hardware advantages to run faster on standard arrays. Merge sort dominates specific, non-contiguous abstract data structures. Choosing an algorithm relies on a strict checklist of project constraints. This matrix consolidates the evaluation vectors we've explored. The heuristic is clear. You deploy merge sort when dealing with linked lists, or when absolute stability and guaranteed maximum time limits are non-negotiable, accepting the heavy memory overhead in return. You deploy quicksort for standard arrays, where low memory consumption and raw hardware-level speed outweigh the mathematical risk of an n-squared worst-case scenario. We will take this divide-and-conquer framework and apply it to a completely different class of problem in our next lesson, Strassen's matrix multiplication. Selecting the right tool involves weighing the physical and theoretical boundaries that dictate execution for a particular system.